Welcome to Biomaterials. What are we going to talk about today? Today we're going to talk about, well, we're going to keep it natural, we're going to keep it sweet by talking about natural polysaccharides. Which are polymers that are sort of fabricated by humans or by other organisms, and their repeat units are basically sugars. So sugar rings that repeat over and over and over again, and they're covalently bound to one another. Polysaccharides, these are polymers just in the same way that we've talked about a lot of other polymers. The first one that we're going to talk about, we hinted briefly on in the last lecture, but the first natural polysaccharide that we're going to talk about is alginate. And when we talk about alginate, we're going to talk about a few sort of physics-y, chemistry-y things that go along with it. We're going to quickly recap its cross-linking mechanism with calcium ions. So it's calcium cross-linking mechanism. We're going to go into a little bit more depth than what we sort of briefly hit on yesterday. We're also going to sort of make some discussions of like whether other ions could potentially cross-link alginate. And then finally, we're going to talk about the effect of pH on the gelation of alginate. And this is a really cool application because you can basically create pH responsive hydrogels with alginate and other molecules as well. And you can use these for like drug delivery. So for example, you can keep your hydrogel tightly bound up at the pH of the stomach. When it passes to the intestines and the pH raises, then it can, expand and release. It can reduce its cross-linking, etc. Right? So, in particular, pH can affect more than just there's pH that can affect swelling and pH that can affect cross-linking. Today, we're going to discuss the effect of pH on cross-linking. And in particular for alginate. Then we're going to talk about another natural polysaccharide, which is pectin, and how it's similar to in some ways and different from alginate in other ways. So we're sort of going to draw some comparisons. Pectin is a different polysaccharide from alginate, but they have they're similar in many ways. And by looking at sort of how they're similar and how they're different, that will also kind of help reinforce some of these ideas that we talked about with alginate. Then we're going to talk about two more polysaccharides, Chitosan, or chitin, and chitosan. And when we talk about chitin and chitosan, we'll talk about a few concepts. When we talk about them, we'll talk about the side group. We'll talk about the side group and the effect of how side groups on these polysaccharides can affect solubility. So solubility. And we'll also talk about how different side groups on chitin and chitosan, for example, compared to alginate and pectin, affect the cross-linking process. So side group and its effect on cross-linking. So without further ado, let's talk about alginate. So alginate's a pretty cool molecule. It's a polysaccharide that looks like this. And again, you won't be expected to memorize molecular structures in this class. So I'm going to write down a molecular structure. Don't be expected to memorize it. But by identifying key features on the molecular structure, I want you to be able to sort of make inferences or make predictions about what the behavior of these things might be. So let's sketch out what alginate's repeat unit looks like. So we have an oxygen. This oxygen's connected to a carbon, another carbon. This carbon goes up here, and there's an OH and an O like this. This carbon is connected to an oxygen, down to another carbon right here, out to another carbon right here, and this carbon has an OH group on it, down to another carbon right here that has an OH group on it, and this carbon goes back to this one right here, right? So there's carbon, 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 right? So it's basically made of a six carbon sugar, and this carbon right here is connected sort of off to the next one. So if we look at the repeat unit would sort of be defined here. And I tried to draw this in a sort of 3D way, right? Because these are all single bonded carbons that are all sort of slightly out of plane with one another. There are a bunch of hydrogens here that I omitted, right? This carbon basically needs an extra hydrogen, as does this one. This one needs a couple. This one needs a couple. Or sorry, this one just needs one more, etc. Right? So there are a bunch of hydrogens that I haven't drawn here. But anyway, this is what we have here. So what's the key thing? So what's the key feature of alginate? Well, if you look at this carbon right here and the COOH, what is this? Well, if you dust off your maybe first year biology or your high school chemistry or something like this, you'll recognize this as carboxylic acid. And if you know this carboxylic acid group, it's a weak acid, right? So it's a weak acid, and weak acids sort of exist in an equilibrium state where they're protonated or they're deprotonated. So a carboxylic acid group has a COOH, and this exists in equilibrium with its deprotonated state, where it's a COO- and an H+. And I guess, strictly speaking, there's a water on this side, and this is H3O+, but again, let's just pretend that it's H+ right here. So there exists an equilibrium here, and basically the pKa of this weak acid determines sort of like what ratio, what the ratio of protonated to deprotonated state exists. What key feature does this lend the alginate? Well, if you imagine it's, not all of the sugars in the chain look like this. Some of the sugars have this COOH where it's just COO-, right? So basically some of these deprotonate. And if you were to sort of zoom out to the scale of these chains, right, if you can imagine a whole bunch of these sugars all linked together, so we basically end up with these chains here. Periodically, at least some of, the H+ goes and floats away and does whatever, but some of these points along these chains end up negatively charged. And if you can imagine, if I add to this solution some calcium, if I basically add some calcium salt, then I'm going to basically be putting in some calcium 2+ into the solution. If you remember, if you picture your periodic table, calcium is in the second column, and things in the first column tend to form +1, things in the second column tend to form a +2. So for example, if you added some calcium chloride, calcium has a +2 charge, so its chloride salt would be calcium with 2 chlorines. If we added it, the chlorines go, just float off in solution, and basically you end up with calciums that sort of have a +2 charge. So we sort of have these so-called divalent, a divalent cation. Divalent in that it has 2 charges, cation in that it's positively charged when it's in solution. Well, basically what happens is you form an ionic bond, because periodically along this chain, we end up with negative charge. The positive calcium is attracted to that. But now locally, we end up with sort of negative, 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 and then a plus somewhere along this chain, and then negative, 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 negative. So another alginate chain that has negative charges periodically bound to it from these carboxylic acid groups. This one, and basically because calcium is plus 2 charges, it can get a -1 from one chain and a -1 from another chain. So this forms 2 ionic bonds, and this basically forms a bridge. That's enough to actually link these 2 chains together. And basically this can create the cross link to form a gel. Don't believe me? Well, you can see it with your own eyes because I created a live demo. Oops, sorry, not salt. Calcium chloride. So what do I have in here? Here I have a 2% weight per volume sodium alginate in 50-50 grenadine with water. Why grenadine? Just because I want it to taste good. And water here. So, you know, if you look in here, I mean, it's a pretty viscous solution, but it's definitely a liquid, right? It's flowing within this container, right? You can see it. You can see it flow. You know, it's a very viscous liquid, but it's a liquid nonetheless. Here I have 120 millimolar calcium chloride, and spoiler alert, this is food grade. This is food grade too. So what can you do? You can take some of your alginate solution, which is a liquid, right? It's flowing. You can see me scoop it up in this spoon here, and I can dunk it into the calcium chloride solution. So what's going on here? Well, I'm going to drop some in. You see it just created a big old blob right there. Maybe I'll do another one. And if I give those a minute to rest, what's going to happen? You know, we started off with this situation, and if we don't have these calcium ions, these negatively charged chains will just repel one another. So they can flow past one another very readily. I mean, it's viscous, but they can still flow past one another, and that's what I have in here. When I dunk a blob of this into the calcium solution, the calcium ions start to diffuse into the alginate blob that I've put in, and these calcium ions basically cross-link the alginate all along the surface of these blobs. So if I give them a minute to solidify here, which I've done, I can scoop them out, and you know where they used to be liquid, now they're solid blobs, or at least the outside is a solid blob. The inside is still liquid because the calcium didn't have a chance to diffuse all the way into the interior. So I can, you know, poke open the outside. And what is this? These are essentially DIY gushers. I don't know if you remember those candies, gushers. But you can eat it. Delicious. I'm gonna eat this one too. So, alginate, you know, it's you know, I can eat it. Calcium, there's plenty of calcium in my food. Nothing wrong with that. So I can create these, there's this whole burgeoning field called molecular gastronomy, which is basically a whole bunch of chemistry nerds making cool food, and alginate is one of the things that you can do in there. So, and you can, you know, you don't need to make just blobs, but you can actually like put things in a syringe, and you can make like weird spaghetti. I mean, it's not really spaghetti, but, you know, you can make weird spaghetti. You can string it out. Oh, there it is. Look at that. Wild. I'm going to eat this one, too. Excuse me. Oh, but you definitely want to blot off the calcium water there, or the calcium solution tastes a little salty. So you're definitely going to want to blot off the salt water before you do it. So there we have it. You can see with your own eyes the formation of calcium cross-linking. So let's take a look. Let's imagine if we had other ions in this solution. So let's say instead of using calcium, so let's bring back the solution right here. Let's say instead of having calcium for cross-linking, I tried to use sodium. So take a moment now, pause and ponder. What if I tried to cross-link with sodium chloride, or NaCl? What would happen if I tried to do that? Well, hopefully you've had a chance to pause and ponder. I brought some sodium chloride as well. So let's see what the effect is there. I'll syringe up a little bit of my alginate solution, and I'll squirt it into this sodium chloride. So take a moment now, predict what will happen. All right, I squirted it in. If you remember, the calcium, when I squirted it into the calcium chloride, it formed basically spaghetti when I pulled it out. But in the sodium chloride, well, I mean, there's a little bit of structure to it. But if you see, my fork, you know, eventually it just sort of oozes right through my fork. Right? So I'm taking my fork, I'm trying to scoop it through, but it just sort of oozes through my fork. So it's not any more solid than when I started it, just in the solution with itself. It turns out that, you know, the tiny little bit of gelation that you see here is basically because the water coming out of the tap in my house has very small amounts of calcium just inherently dissolved in the water. If I did this with DI water from a laboratory, then you wouldn't you know, it would just dissolve completely. You wouldn't even see hardly any gelation at all. So, you know, what happens? We don't observe this cross-linking. Oh god, that was salty. We don't observe the cross-linking when we use sodium chloride. Why not with sodium chloride? Well, just imagine what I have here. If I had sodium, if you remember, sodium is basically just a plus one charge in solution. So if I put some sodium in here, you know, one of my sodium ions goes here and essentially neutralizes that charge. Another one of my sodium ions go here and essentially neutralize that charge. So there's no reason for these chains to bond to one another. There's no reason for them to bond when I use sodium chloride. I basically need that +2 charge to get the -1 from one and the -1 from another. So we basically get no cross links. No cross links when it's sodium chloride. Let's now take a look at the effect of pH on cross-linking. So let's look at 3 scenarios when we think about pH. So pH on alginates cross-linking. So let's look at scenario 1, where I have a very low pH. Scenario 2, where I have a moderate pH. And scenario 3, where I have a very high pH. And so take a moment now, pause and ponder, under which of these circumstances do you think we would expect gelling? So which option yields a gel? Well, let's talk about the very low pH first. So very low pH, what does this mean? This means lots of H+. Right? If there's lots of H+ in solution, then that means, you know, due to, what was it, Le Chatelier's principle or something like that, if there's lots of H+, then the system is going to try to re-equilibrate. That drives the system towards this state. So lots of H+ drives towards COOH. If I have this state, can there be any cross-linking? Well, if it's COOH, then this means all the chains are neutral. All the chains are neutral charged, right? So instead of having these chains with a bunch of minuses periodically all along it, if I have too much H+ in solution, I drive the equilibrium towards this. All the chains are neutral, and basically means there's no sites for cross-linking. And that basically means that calcium can't really cross-link. When you have too low of a pH, calcium can't really cross-link alginate. Let's now, so take a moment now, pause and ponder. Think of what happens at very high pH. Well, at very high pH, we have almost no H+. Right? That's basically what a very basic solution would be. So if we have almost no H+, then almost all of the COOH groups will deprotonate to form COO-, right? So this means this drives us towards nearly all groups with a COO-. And what does that mean? That means the chains are very negatively charged. And probably, if you can imagine, if these chains are just too negatively charged, even if a calcium ion comes along, there's still too much chain-chain repulsion for these chains to get close enough for the calcium to form a cross-link. So unless calcium concentration is super high, so unless the calcium 2+ concentration is super high, basically there's too much repulsion to overcome. And what does this mean? This means you basically get no gel, no cross-linking. So what does it mean? It basically means there's this sweet spot at a quote-unquote moderate pH, and exactly what that pH is depends on what the pKa of that weak acid is. But at a moderate pH, there's basically enough sites to form crosslinks, but not too many to result in excess repulsion. So that's basically the effect of pH. So this is basically the effect of pH on cross-linking. And it all has to do with how extra or depleted H+ drives this chemical equilibrium. So that's alginate. Thus concludes our discussion of alginate. Let's talk about pectin now. So pectin is also a polysaccharide. So pectin's also a polysaccharide, and it looks something like this. So there are essentially two types. It's essentially a copolymer of two types of repeat units. So it's a copolymer. And that there are two types of repeat units. One type of repeat unit that looks like this. So there might, you might have a stretch where, let's say you have n of these repeat units. And then you might have another stretch where you have m of these repeat units, and the ratio of n to m sort of depends on certain situations. And these two repeat units look very similar to one another, except for this one change right here. So, what are some key features to look at? Well, this should look pretty familiar. This is a carboxyl group. And it's just like alginate. It's just like alginate, but there's this group right here, which is called an ester. And if you looked at it sideways, right? If we remember the lecture on polyesters, right? Polyesters have that C double bonded to an O, single oxygen bridging off to the next thing. So if you look at it, there's basically an ester bond between the ring of the sugar and this sort of methyl group sticking out here. So what's the key thing with pectin? Well, pectin is similar in many ways. It's similar in many ways to alginate, in the sense that alginate pretty much looks the same as this, a sugar ring with a carboxylic acid group. It's just pectin is the sort of like less effective cousin compared to alginate, in that this ester group, basically the presence of this methyl group, means this guy doesn't. This is not a weak acid. Not a weak acid. So basically, unless you go to some really crazy extreme pH, this neither protonates or deprotonates or whatever. This is sort of it's just along for the ride. So basically, it's pectin is similar to alginate in that it forms negative chains and you can cross-linkate with calcium and all that stuff, but only a fraction of the sugars along the chain are participating in that protonation deprotonation. So basically, it's it's similar to alginate, but because some of the groups look like this, it basically means its gelation is less extreme or less pronounced and sort of less pH dependent. So where might you have encountered pectin? Well, pectin is a polysaccharide that exists naturally within plants, and in particular it exists within fruit. So if you've ever had some fruit jam, for example this fruit jammin, this strawberry jammin right here, and you look at the ingredients on the back, you might come to pectin solution as one of the ingredients. And the pectin solution is made of water and fruit pectin. That's basically what's going on right here. So fruit pectin, so this basically exists in fruit, and we use it in jams and jellies, We use it in jams and jellies to create a delicious texture. So if you want to make certain fruits or certain jellies, some fruit naturally has pectin in it, but other types of fruit does not have pectin in it. So for example, if you want to make certain types of jelly or jam with fruits that don't naturally have pectin, you can basically buy pectin, like a little jar of fruit pectin. It's a powder, and you can scoop it out and add it to your jelly recipe to basically make jellies out of fruits that wouldn't otherwise be able to form a jam or a jelly, because those fruits naturally don't have pectin in it. So some fruits naturally have pectin, some fruits don't, but you can buy pectin to add to your jams and jellies to thicken them up and give them a delicious texture. Really, I can't say enough good things about yummy jams and jellies and the pectin involved. But enough about yummy foods. We need to finish this lecture. So let's talk about chitin and chitosan. So chitin and chitosan polysaccharides as well. So where might you find chitin? Chitin is a structural molecule found in insect carapaces or in insect exoskeletons. So basically insects, bugs, they walk around, they have that tough bug armor on the outside. Chitin is one of the main molecules that makes up that structure in their shells. So, chitin, has, in its various forms, it has remarkable mechanical properties. And so what does chitin look like from a molecular structure? So chitin looks like this. It's an oxygen right here. Oxygen. OH group right here. This is bonded back to nitrogen. So it's it's a polysaccharide, right? There's a ring-like structure here. This goes off to the next one. But down here, there's this NH. So N being a nitrogen, there's an H sticking off of the nitrogen, and sticking off this nitrogen is this kind of wacky thing right here, with sort of a CH3. So chitin is basically this thing right here, repeating over and over and over again. Chitosan is a modified form of chitin, where the way we make chitosan is we often start with chitin, and we basically chemically treat it to remove this thing right here. And this thing right here is a so-called acetyl group. So there's this group right here that I've highlighted in yellow is an acetyl. It's an acetyl group. So through deacetylation, you can take chitin and you can deacetylate it. Again, the details of exactly how that is accomplished is a little beyond the scope of what I want to cover now, but you can deacetylate your chitin to form chitosan. And what does chitosan look like? Well, chitosan looks almost the same as chitin. The basic ring structure is unaffected. Its interactions with its neighbors are unaffected. But basically, instead of having this acetyl group, you instead just have NH2. And that's the repeat unit of chitosan. And of course, there's essentially a continuum between chitin and chitosan, where you could start with chitin and deacetylate only some fraction of the chitin to form chitosan. So you can deacetylate all of them to have totally chitosan. You could deacetylate none of them to have chitin. You could deacetylate some fraction to basically have some partially deacetylated structure. So what's the key thing here? Well, what's this group right here? What's this? What is that going to do? What will this do? Do in solution? Well, if you dust off your like first year biology or your high school chemistry or whatever, you might look, this looks similar to ammonia in some ways, right? Ammonia is NH3, and when ammonia is a base, so in water, NH3 reacts with water to form NH4 plus and OH minus. this NH2 group can sort of do a similar thing. So if you have an NH2, it's a weak base. So this is a weak base. And what does that NH2 do? Well, basically that NH2 reacts with an H2O, where these two come together. Sorry, this is not a minus, but rather like the whatever this is bound to. This NH2 reacts with this H2O to form NH3 plus and an OH minus. So in a sense, chitosan is kind of like the opposite. It's like the evil twin of alginate, right? Alginate had this situation where it had this COOH, and in water it became negatively charged. This amine group sort of does the opposite. When it's in water, it becomes positively charged. So what's the key takeaway here is this means that chitosan chains get positively charged. So what's the cool thing? So what's the cool thing about chitin and chitosan? Well, this positive charge basically has two effects, and part of its effect is on solubility, and part of its effect is and its other effect is basically how we treat it in terms of its cross-linking. So the key thing with this positive charge is it basically means that chitosan positive charge basically makes water super attracted to it. You know, charged is sort of the most version of polarity, right? You know, polarity is sort of like partial charges. If this gets totally positively charged, then water really, really loves to cling to it. So basically, you know, what is it? So there are sort of two effects. So one is it basically, you know, this effect of charging means that it's more hydrophilic, and basically it becomes so hydrophilic that it becomes soluble in water. And there are basically some cool tissue engineering applications like that. So, you know, for example, you know, here I had this alginate, and the alginate was soluble in water. And, you know, I was able to basically go from a liquid to a solid only with some calcium for the alginate. There's cool tissue engineering applications there. You can follow a similar process with chitosan, where the chitosan is soluble. You can mix it with some cells. Only instead of cross-linking instead of cross-linking with calcium, which has a positive charge, you would need something with a -2 charge to basically cross-link that chitosan. So you can basically dissolve it in water, and there are cool tissue engineering applications where you can basically cross-link the chitosan with something that has a -2 charge, and that cross-linking process is similar to alginate, gentle enough to cells where you can you know, essentially do 3D printing or injection molding of cells while suspended in these solutions. So there's really cool bioengineering that can be done there. So the cool thing about deacetylating the chitin versus the chitosan is, you know, this acetyl group is a little bit polar, but definitely not as polar as this. So chitin is basically not very soluble. You know, good luck trying to dissolve, you know, bugs would not be very successful in the world if their exoskeletons were constantly dissolving in water every time they got wet. But we can basically treat this chitin to make a soluble version of it by replacing something that was only a little bit polar with something that is the most extreme case of polar, i.e. charged. The second thing, so basically this makes it more hydrophilic, more soluble in H2O. And then the second thing, this means that now we get positively charged chains. This means we can cross-link chains with things that have -2 charge ions. So there exist ions out there with a -2 charge, and it turns out that you can basically use these -2 charged ions to cross-link chitosan in the sort of opposite way that we use +2 charged ions to cross-link alginate. So, thus concludes our discussion of a few natural polysaccharides. The next lecture, I'll talk about a few more, and hopefully this has revealed some of the cool mechanisms by which we can cross-link these things, some connections between differences in the atomic structure and how cross-linking or other things might be affected, and also some idea of how it's not just the chemistry, but the environment that it's in, where we can sort of drive equilibrium one way or the other, and how pH might affect the cross-linking of these polysaccharides here for their engineering or other biological use. Thanks for watching, and good luck with your study of biomaterials.